t-shirten då alltså. Jävlar alltså. Du diggar den? Ja, stolen i ögonen. Ja, blir påtagen. Ja, blir påtagen. Så det brukar vara. Ligger och blir påtagen.
Det är så det fungerar.
Oftast. Idag är det t-shirt.
Det var ju så kul.
Jävlar!
De var inte så med.
Jag tog en hel med.
Och Norrlands har ju fått den här smakar annorlunda. De var ju 5.
Oh, det är
Hur mycket du är såhär, en apelsin du är som smakar kanske. Men det är nej, men jag känner
besvikelse var ju det. Är det ofta så?
Okay, let's get started. Today's topic is essentially about continuing on from the central limit theorem and how the central limit theorem actually applies to the maximum likelihood estimator, which in turn will help us do confidence intervals for parametric experiments. And then we will see the wall test, which is a very simple hypothesis test for parametric experiments. And I will maybe have time to introduce you to some of the same concepts for non-parametric experiments. Right, so how do you do an estimate in an infinite dimensional non-parametric setting, and how do you do a test? And these kinds of tests are called permutation tests. And in the industry today, they're called A/B tests when you're trying to determine if a set of users are actually behaving differently according to certain parameters. The other thing I just want to briefly touch on is the maximum likelihood estimators we've seen. I've shown you with symbolic methods, or you can do it by hand, but often the problems will not be so simple. So because you've had some introduction to scientific computing, and I think next semester or next year you'll see optimization, right? You'll take a course. So it's good prep for it. And the ideas are really simple. You're just doing some kind of gradient descent using Newton method, basically, some souped up version. So once again, from the point of view of how do we use this particular numerical method to solve an MLE, I've given plenty of examples here. What we really need to do is simply apply the method for the expression, the likelihood expression itself. So let's look at a quick example. Let me see. So these are just symbolic stuff. The exam is going to be very similar to the sample problem, so I don't think you need to really worry. I will probably not teach this course ever again, so no sweat. There'll be Swedish version and English version. You make your decision as you enter, and you'll be seated according to the rules. Okay, the Swedish version has the Swedish rules, and my version has its open book, open notes, and open notebooks. And the manuals are trained, so you should not have any problems. Yes, you will get a hard copy of the 3 or 4 steps you need to do to submit the exam in the English computer version. And so you don't have to memorize the steps. And yes, if you just go through the sample exam questions in that order, I will just change some questions because that's what most of you are comfortable with, and so it should be fine. There should be no issues with the exam. Okay, so let me just tell you. So we looked at these timestamps last time. So let me find out where we can get into the numerical solutions here. The ideas are actually really simple. I think it's somewhere here. Yes. So assignment 3, problem 2 is about finding the MLE of the exponential random variable. And here, this is using a symbolic method, right? You can just do it by hand and put in the expressions. So here, yeah, that's my version with the solution. But anyway, numerical optimization for finding MLE is the main stuff. So what's the idea? We use a built-in method, right, which you will learn in detail later. So it has a lot of methods. Nelder-Mead is a particular method to find the minimum on an objective function. So we are interested in finding the maximum of the log likelihood. So we simply take the negative of it. So then we can just turn it into a minimization problem. Just find the minimum of the negative of the log likelihood, which will be the maximum likelihood estimate. So now, of course, there's a whole lot of methods, and these methods you really have to study a lot more to appreciate it, or just at least one more course. But these are the ones I think are going to be used by default. So this is a Broyden-Fletcher-Gano-Shano algorithm. This is a Newton conjugate gradient method, and this is some low memory version of it, and this is sequential quadratic programs. And so you'll see this in detail later, but for now, just pretend it's some black box that's going to give you an answer. So this is what I said, argmax of the log likelihood is nothing but the argmin of the negative log likelihood. So the argument that minimizes the negative of a function is the same argument that maximizes the function. So here is a little bit of a show URL. If you want to get into a bit more details, you can sort of look at it. So what are the main concepts? We have an iterative algorithm, and the algorithm has an initial condition, just like solving the roots of an equation using the Newton method. And then in 1D, you look at the slope and just keep cobwebbing. Every iterate, you keep moving toward the local root. The same way in high dimensions, you use gradients, okay? And you just follow the direction of the steepest descent in the minimization problem. So some problems are said to be well-conditioned, like if it's a perfect, x square, and you're trying to minimize x square, it's a quadratic. You start wherever you like, you're going to always end up in the valley. There's only one valley, right? So the global minimum is the local minimum in those settings. Of course, if you have x square and then I compose it with minus 10, 10 shifted x square, so I have two valleys, right? And I have some temperature terms, so it's really messy. Then, of course, depending on where you start, you're going to end up in the local valley, right? That's called sensitivity to initial conditions of the local optimization algorithm. So these things you will learn later, but just be aware the starting conditions will determine things, but all the examples we'll see, they're well-behaved problems. Okay, so depending on what kind of problem it is, different methods should be called, and a lot of this is sort of heuristic, so there's not a mathematical proof unless you make strong assumptions, okay? So conjugate gradient descent is one of these methods. Have you guys seen this already in scientific computing? Yeah, no? You saw it in 1D, right? Newton-Raphson. Yeah. Oh, good. So it's just basically the same idea. You know fair bit of linear algebra now. Just think about gradients, which is all slopes in every dimension, and then you just, you just follow the gradient. So the idea is generalized, okay? I kind of don't want to delve too deep into this because you should really learn it from your optimization course, and you will later on. So for us, let's just try to use these techniques in a hurry, right? In Sage Math, which is this Python wrapped stuff, to solve problems. So here is a optimize, minimize scalar method. So if the function f of x is going from R1 to R1, if its input is one dimension, then in SciPy or Scientific Python, you use this minimize underscore scalar function. And for all other functions where the domain is more than one dimension, then you use just this minimize method. Okay? So one dimension is special. So that's what we're doing here, and this is straight out of the docs, so you can check it out later. And I'm simply defining a function to be e to the minus x minus 0.7 squared, right? I just relocate x to 0.7 and then I square it. So it's just a quadratic centered at 0.7. So I'm going to start somewhere and see where it goes, right? That's exactly this example. So I'm going to call my result to be optimize.minimize scalar of this function f I just defined here. Okay, and then I just want to print the result, whether it succeeded or not, because it has a little Boolean that keeps track of whether the algorithm thinks it succeeded, okay? And then xmin is just result.x. And you can just print this. So let's see what happens. Okay, it says it succeeded, and it said the argmin x. That means the argument x that minimizes the function f of x is nearly 0.7. Okay, and this is floating point numerics. Okay, the other thing to notice is this np.exp, right? So you guys are used to MATLAB or array arithmetic. So if x is an array, then np.x numpy.exp will apply the exponential function to every element of the array. Okay, so you have to think in sort of array operations. Okay, when we use np.exp. Here it's not a big deal. Later on it'll become more important. Okay, so I'm just plotting this function just to see. Yeah, it's just x squared translated, and the minimum is at 0.7. Okay, so then you can also plot result.fun, which will return the value of the function at the end of the iteration. Like when the algorithm say started somewhere, it jumps around and it stops, and then it tells you the value of the function. So this is the minimum value. And then result.nfev is the number of function evaluations. It did 13 iterations, okay, or 13 function evaluations, and the number of iterations in the algorithm is 9. And it's because it's probably using the function itself to find the gradient, and don't worry about the details now, because it uses something called finite differences, right? To find the slope of a function at a point x0, you evaluate the function at x0, at x0 plus delta, divide by, x minus x0, or delta. So this is called finite differencing. It's an approximation of the slope of the function nearby. So if you don't have an expression for the derivative of a function directly, right, that you do by hand or symbolically and give it, it'll just use finite differences to find the slopes, gradients. Okay, the next thing we really want is bounded one-dimensional optimization, because we're interested in maximum likelihood estimate, or minimizing the negative log likelihood function. And the parameter values for statistical experiments or probability models are going to be in some constrained space, right? Like theta for the Bernoulli experiment is in the unit interval. So we have to do something about this. So that means when we do our optimization, we have to tell the optimization algorithm, don't look for the answer outside some bound, some interval or some rectangle in higher dimensions. Okay, so that's exactly what this thing does. Bounded one-dimensional optimization. Here we use exactly the same function, just to learn syntax. I just use this thing called bounds. So I put an interval. I only am interested in answers between 0 and 1. And yeah, method bounded you can call, or it'll find one by default. Okay. Of course, you have to tell its initial condition, where do you want it to start? And that initial condition for the optimization algorithm should, of course, be inside the bounded interval, right? So you say, find me an answer in this interval, so you should start it somewhere there. That's all I'm doing there. Maximum likelihood estimate using optimization is basically the thing here. What do we do? So let's say we look at the sample waiting times problem, right? This is actually Joshua Fenmore's data about the orbiter waiting times in Christchurch. And it's just up to minutes, right? So this is the data I collected. And I'm just going to call that the data. And then the task is to implement the negative log likelihood of this exponential IID experiment. Okay. So you see, this is slightly different. What I'm now telling you is, here's the data. Just find me the lambda hat, the MLE for the rate parameter for this data, you see? And what we did before is different. You just abstracted away the data, and you said, here's the likelihood function. I solve for it analytically, right? And I find the MLE. And then, so now, no matter what the input data is, I can use this MLE expression, right? It's a function of the data. So for this example, it was just 1 over the sample mean. So no matter what the data is, I find the sample mean and do 1 over sample mean. Here, we're doing it differently. Here we're saying, here's all the data. Get me a numerical expression for the likelihood for this specific data, and then hunt the MLE using using the minimizer, the minimum of the negative log likelihood function. This is what Google does, this is what Facebook does, and so on, right? Of course, not for a waiting time problem. They'll like put images and whatever, your social media chats and all sorts of things. So on the news, there is something quite interesting going on, at least in the US, right? Facebook has some interesting propositions about essentially being able to preempt what you will be doing. So this is called, it's like a new industry, futures of human behaviors, right? There's a lot of interesting things happening. But anyway, in all these problems, what they do essentially is this kind of philosophy. They will actually take the raw data and then they will fit some model to it, right? They will do a lot more than just the likelihood. There will be penalty and things like this you will learn in statistical ML. So that's the main idea here, right? And I think I just gave you the answer here, right? So you don't have to be too worried in the exam. It'll be probably a problem like this. You just have to only do this, right? You have to write down the negative, well, there's negative, log likelihood function. So you know what that is. You just logarithm. You sum of the logs, and you just put the likelihood for one of the data points, right? So this is lambda e to the minus lambda times x. But because we're doing everything in array arithmetic, np.exp, right? exp gets applied to every term, right? So this multiplication, param lambda is a scalar, and then when I do this asterisk, it just multiplies the scalar to every entry in this big array. Because you see, I've made this an NP array, an NumPy array, so it's like MATLAB. So you just have to slightly think in array terms, and then you're done. Right? So now this guy, for every value of the parameter lambda, it's going to give you a likelihood value. And that's all the optimization, the numerical optimization routine needs to know to crawl and find an answer, right? That's all we're doing. Okay, so let's see what this guy does. Solution found, number of functions 12, and it's giving me 0.11, which remember for this problem, this is also the answer when we did it analytically, okay? Up to some last digits here. So, okay, I think there's other details, like there's a default tolerance. So just like in your one-dimensional Newton-Raphson routine, you stop the iteration once you've gotten arbitrarily close to the answer, right? The absolute difference between consecutive values in the domain are less than some e to the minus whatever, 60, or some tolerance, right? It's exactly the same idea as going on here. So you can play with those things if you want more accurate answers. Okay, so assignment 3 is basically exactly the same, but now you just have to do it for the IID, for the Bernoulli example. Right? This is not difficult. Yeah, here's a solution, so you can pause the video and find it if you want, okay? So multidimensional constrained optimization is the next main idea, right? So multidimensional constrained optimization is exactly the same as bounded 1D, except now we are in 2 or higher dimensions. So how do you introduce bounds? You just put a box, right? Rectangle, square, cuboid, hypercuboid, and you can even put general constraints, which you will learn in your scientific computing course later. So these can be arbitrarily complicated constraints up to arithmetic specifiability, right? So here is a little example. We have f of x1, x2 is simply square root of x1 minus 3, x2 minus 2, the whole squared. So we just centered at 3, 2, you see? And you're seeing the contour lines of this, this function. This is the square root of a quadratic centered at minus 3, 2. So of course, now we introduce this bound. We're only interested in the argmin of x1, x2, right? 2 numbers that live in this box, minus 1.5, 1.5 squared, right? So it's just this box right here. So I start somewhere, and then my game is to find the minimum of this function while never leaving this box. And that's what this is doing. It's sort of iterating and finding something here. Okay. So if you sort of chase these links, you'll really drop into as much detail as you want all the way down to the C and Fortran codes, okay? So we can use this iterative if you want. So you can use this iterative numerical method to find MLEs. So I put this lowercase e because everything is now estimate. It's based on the sample itself, okay? So what are the steps? You basically have to find the numerical expression for the function f. That's it. And this f should be the negative of the logarithm of the likelihood function. And you use the data set itself because you need numerical values. This is not symbolic. And you need the parameter bounding box that you know from the model. Right? Bernoulli is 0, 1. If it's theta 1, theta 2, it's a little more complicated, right? If the uniform theta 1, theta 2, it's more complicated. I won't give that in the, because it's the half plane, right? Or whatever. Lambda for the exponential is the positive half line. Of course, when you do numerics, you cannot specify it's between 0 and infinity, right? Because the largest double is finite. So you just try 100 or something and see what happens. If the MLE hits the boundary 100, then the rate is, maybe bigger, so you play around, right? So there's a lot of, it's just floating point arithmetic stuff. So yeah, and things can be unstable. If you say lambda for the MLE, for the exponential, if you say lambda's left bound is 0, you're going to have crazy issues with the logarithm, right? Logarithm of 0 will crash to minus infinity. So maybe you have to put the bounds to be 0.001 or whatever. You have to play around. And it's also a function of how many samples you have, right? If you have lots of samples, then things can blow. But I am not expecting you to spend too much time on this in the exams anyway. So here is our example. We exactly do this, except we call this function optimize.minimize, okay? And it's giving me an answer. It's finding the minimum as 1.5, 1.5, which is exactly the corner of that box, right? And it makes perfect sense because this is the lowest contour symmetrically around the center that intersects with this box. Okay, that's and then assignment 3, problem 4 is basically asking you to do this for the normal random variable. So you have n IID trials from the normal, and your parameters are mu and sigma, right? So sigma is standard deviation, so it's greater than 0. Mu is any real number, so there's no real constraints. But if you use this constraint method, then you can make mu to be some kind of big interval, a minus 100, 100 or something, and see how it behaves, shrink it or expand it. And then the same way sigma, if some number slightly bigger than 0 and something big, and play around with it. So that's basically the problem here. So you have to give initial arguments, so where you want to initialize the algorithm, right? What you want the initial mu to be, initial sigma to be. And we also, for this problem, we already know the answer because the maximum likelihood estimate is simply the sample mean for mu. So mu hat is just the sample mean, and the variance is just the sample variance, okay? Almost the sample variance. We didn't do this analytically here, but if you already know the theory to derive it analytically if you want. So when you do the numerics, it should just be okay. Okay, so I told you about this sort of R versus Python versus the JVM languages versus C, C++. SageMath lets you drop into many worlds, so you can do R if you want, but let's all right, let me continue, right? So this is really where I want to be. We are trying to cover set estimation now. Right? This lecture should really be about just this. So point estimates, I told you, are we sort of think of us as little whale hunters. We have this harpoon, and it's this math notation. And this harpoon is really a kernel, a Markov kernel. So you're an experimenter, and you have a decision to make. You have observations, and then you hunt for a point of interest. So the point itself is the parameter in our example. So it's the point, say the unknown theta star, which for the Bernoulli secret experiment was 0.3. We are trying to just take the data and estimate this unknown parameter. And to estimate it, we'll just hit it with like a little harpoon. So this is going to land as a point on the unit interval somewhere. Okay? That's what MLE does. But that's not quite good enough for a lot of problems. It's not good enough for science, right? For science, you need hypothesis tests, and you need a different notion of estimators. So this notion is set estimation. So now instead of just a harpoon, maybe you have like two harpoons, you go boom, and then you say, the true parameter I'm after is going to be trapped inside these two intervals, right, with a very high probability. And that's basically confidence interval in one dimension. And the idea extends, we will see soon, in infinite dimensions as well. Okay, so we went through all of this so that you guys know what's the limit and what's the sequence, and I don't know. I think this is important for engineers to know what formulas are about, because at the end of the day, it's just assumptions. And if you don't know what it means, you will never be able to like throw it out of the window when it doesn't make sense. So that's why I'm teaching like this, okay? I don't want to just give you boxes and do this, do that. So, because, you know, I mean, this is maybe one or two of you, you know, will change the world, right? Like seriously. So some of these definitions are, you know, to make more of you change the world in some sense. Okay, so we saw the central limit theorem. This is where we stopped last time. So you've seen this in your Swedish course. So what are we doing? So you know about convergence and distribution. Right? So you now know what it means to have a sequence of random variables converge in distribution to a limiting random variable. So our basic setup is this. x1, x2 is ID x1. That means they're all identically distributed. And this assumption, by the way, is not that naive. This is exactly the assumption in Google Translate. This is exactly the assumption in facial recognition of every human. You understand this? Because the mathematical model just says there's nothing being said about what the dimension is for this random variable, right? It can live in like, you know, completely infinite, possibly infinite dimensional spaces, right? So it can live over images, and it can live over images correlated with what people are messaging just to their second neighborhoods of friends. And so it's an incredibly general thing. And the idea assumption is the assumption that justifies all the mathematics and the theory of why these algorithms work, right? So it's very, very general. Yeah, although we just see it for simple things here. Okay, so that's our setting, and we have to suppose that the expectation exists and the variance also exists, which means they're finite. So unlike Cauchy, then we have the sample mean x sub n bar, right? Just x sub n bar, the sample mean, and then the statement is that x sub n bar converges in distribution to the normal random variable whose mean is just the expectation of x1 itself, or any of them, and whose variance is just the variance of x1 divided by n. Okay? So as n increases, the sample mean is concentrating, right? Because the variance is just getting smaller. That's the statement. And if we use z to be the standard normal random variable, it means on variance 1, then z sub n is defined like this. It's the you just take away the center and divide by the standard square root of this. So this is called centering and rescaling, or standardization operation. Then when you do this, then this thing is going to have, it's going to converge to the normal. Okay, so these are all equivalent statements. Okay, and we don't need to worry too much about them. We will mostly see it in this form. So once we take the sample mean, subtract away the expectation, and divide by the standard deviation, then it converges in distribution to the standard normal. Right? So it's just a correction so that when n increases, if you look at it raw, it's going to be really crashing in. So we have to just blow it up by root n so that it's, again, normal 0, 1. That's all. So this is it. This thing, to prove this, formally is beyond the scope. But we do this in probability 1 in the math department. Okay, so here is some example, and we saw these little interacts, right? So the amazing thing is the following. Suppose I do 100 replicates, and I increase my sample size, increase my bin size. right? And my theta I set to be whatever I want, say 0.45. So what's going to happen is as I increase my replicates, I get more and more samples. And I'm going to essentially have, if I look at the distribution of the sample means for the Bernoulli's, it's going to be centered around whatever I want this to be. And then the shape will become Gaussian when I keep increasing this, and n can be large enough. So the other remarkable thing is this, or I guess the main remarkable thing is this: if we have any random variable which has finite mean and expectation, so this is exponential with rate parameter lambda equals 0.1. Once again, for this guy, the sample, let's say we have 1,000 replicates, and increase this. This guy is also going to have a Gaussian shape. So Bernoulli sample means, exponential sample means, and whatever else that has finite mean and variance, it'll have this property. All right, sample mean, yeah, it's all right, but what we really want is something much more generic, right? Because I told you the maximum likelihood estimator is a very general object, and unfortunately I won't have time. I might just do some extra stuff for those of you. So I told you that even for the double pendulum experiment or some ODE, with some vector fields, which you guys already are learning and stuff, you have a parametric family as well. Here the parameter takes you to some solution, right? Some x of t with some initial condition. This is the initial value problem. So if your data is actually observations of some trajectory, right? And then you can solve the initial value problem through integration, and then assume that these noises are there, which we will get to in the very last lecture for regression. Then you can actually use the MLE to find the parameters of your dynamical system, okay? And you can start controlling things as well. That's what one of the whole division in IT does. So all of that is MLE theory, okay? So now what we are saying, what we want to know is, can we have something more general about the properties of the maximum likelihood estimator in general? So then we come back to this setting, or sorry about this. So we have x1 through xn. So we have this basic experiment, or IID experiment, except it has either some distribution function or some mass or density function. And the parameter space is finite, right? So theta star is our secret stuff. So we say it's unknown and the law that dictates the observations. And we saw the argmax of the log likelihood is the MLE. So property one is about the asymptotic consistency of the MLE. This is why we introduced the definition of convergence and probability. So what this says is, as n goes to infinity, the random variable, which is the maximum likelihood estimator, right? It's random because if you repeat the experiment, you get a different data and you get a different MLE, right? Maximum likelihood estimate. So the estimator is random, and it converges in probability to the true theta star as n goes to infinity. So that's a minimal requirement of any estimator, right? So the next thing is MLE is equivariant. This is very, very useful. Equivariant, all that means is maybe you're not interested in the parameter theta, okay? But you're interested in some function of the theta, right? Maybe if theta is this, you will get this reward. If theta is that, you'll get this reward, right? This is baby financial mathematics, right? So often you'll be interested in function g of theta. So the nice thing about MLE is that if you want g of theta star, then all you have to do is apply the MLE into g. So g of theta n hat is the MLE of g of theta star. That's cool. That's very powerful. Convenient. So the third property is that the MLE is asymptotically normal, right? This is why we introduce a central limit theorem and convergence and distribution. So you can kind of appreciate this, right? At least animation level, simulation level. So the MLE is asymptotically normal, means theta n hat minus theta star divided by this special guy called SEN hat, which is called the estimated standard error. This will be in the exam, computing estimated standard error. So what is that? Come to that in a sec. So if you do that, then that quantity is normal 0, 1. Or equivalently, you can say the MLE is distributed as the normal random variable whose mean is theta star and whose variance is the square of the standard error. So what is SEN hat? It's an estimate of the square root of the variance of the MLE. Because MLE is a random variable, it has a variance, it has square root is just its standard deviation. So standard error is nothing but the standard deviation of this estimator. Okay? So, and this works for anything. And remember, theta and hat doesn't have to be just the sample mean or inverse of it for baby examples. It can be much more complicated. Okay, so how do we compute this quantity? Well, SE and hat is really this. It's the square root of 1 divided by this really scary beast here, right? It's not really scary. So this thing is called the expected Fisher information. Right? So what is down here? Expectation of the negative of the curvature, right? Negative of the second derivative of the log likelihood function. So the log likelihood function is like this, right? And if it's really peaked, right? We saw simulations when n increased, it becomes peakier and peakier, right? So, and then the MLE is where it takes its maximum. So if you look at these, the rate of change of the rate of change, and it's negative, that curvature tells you something about how concentrated it is. So this is Fisher's insight, right? So, so because of the ID nature, you just have to do n multiplied by the Fisher information of one sample, which is how you compute this. So what do? Well, if it's a continuous random variable, you just have to, expectation just means the integral of the thing multiplied by the probability density function dx. And if it's discrete, it's just the sum over all x's of the quantity times the mass function. Okay, so it's just, so all you really need to get this is simply the second derivative of the log likelihood function, or negative of the second derivative. So find that, and then you find either the integral or the sum. So, and of course, what this means is the usual vert symbol. It means when you compute this quantity, evaluate it at theta equals the MLE value itself, because you don't know what the truth is, right? So you just evaluate it at your MLE. These two properties are, don't worry about it, but we have some other nice properties which are good for more advanced methods. So now confidence intervals and set estimation, right? So what we're going to do is take this simple property, this asymptotic normality property of the maximum likelihood estimator, and then use that for confidence intervals and set estimation. Very basic idea. So, and I told you confidence interval is we're going to try and trap the unknown parameter with a high probability. So I'm going to define C sub n, okay, to be this interval. The left end point is theta n hat minus z alpha over 2 times the standard error. So what is z alpha over 2? That's just the inverse of the distribution function for the normal, right? So you guys have seen this. I'm not sure what, it's the tables that you have in your 100 level statistics course. So this is the CDF of the standard normal, right? So I'm going to say this is my alpha over 2, or 1 minus alpha over 2. So 1 minus alpha over 2, somewhere here. Then I just look at the inverse of this. So this distribution is usually called uppercase p, right, of lowercase z. So this quantity is called lowercase z. Oh man, sorry, this is the Indian z, not the American z. So z sub alpha over 2, right, is this guy, right? Okay, so one minus alpha. Okay, this is what your normal tables are usually like. So normally what you do is you'd be interested in alpha equals 0.05. This is sort of scientific convention. This is like 5%. So what people used to do in experimental trials is if they'll do 20 different trials, because that's manageable, and then they have 1 out of 20 can sort of be off just by chance. So that's where this 5% comes from. So alpha over 2 comes because we actually are interested in something symmetric. So you'll see this. So when we define our confidence interval like this, the amazing thing about the asymptotic normality property of the MLE tells us that the probability that the unknown theta star, no matter what it is, the unknown theta star lying in the confidence interval, C sub n, right? Provided, don't forget the semicolon, provided the model is true, right? Approaches 1 minus alpha as the sample sizing goes to infinity. So that means as n goes to infinity, the probability that I'll trap the truth, okay, under the model being valid is approaching 1 minus alpha. So this is called the 1 minus alpha confidence interval. Okay. So it's just straight out of the central limit theorem. So, and then often, like, you will mostly only do this in the exam. So, that's also a convention. So if alpha is 0.05, that sub alpha over 2 is 1.96. So you just have to remember 2. It's approximately 2. So theta n hat plus or minus 2 times the standard error, estimated standard error, is an approximate 95% confidence interval. Okay. So here is this example I just walked through mechanically. I know some of you don't like to read it, but it took me 2 hours and 15 minutes just to type it. I mean, it's because it's I don't know, it's kind of annoying to do this in the notebook. But so I sort of hope that this means you can do other problems by following exactly the same recipe. So let's get the example for the confidence interval for the IID Bernoulli theta trials. So the specific experiment, so the NIID Bernoulli theta star trials. And we already saw that the maximum likelihood estimate is just the sample mean for this problem. So let's get a confidence interval. So our task is now to obtain the 1 minus alpha confidence interval based on this MLE. So the standard error is just square root of 1 divided by n times the Fisher information of one sample, right? That's this expectation mess. So we want to go there, so that's what I'm trying to get here in the end. So what do I have to do? I have to first find out, because to evaluate this, remember I need to integrate it or sum it over the mass function, right? And what the integrand itself is the second derivative with respect to theta of the logarithm of the mass or density function. So I first start with the mass function, right? And then that's theta to the x, 1 minus theta to the 1 minus x. Log of the mass function is x log theta plus 1 minus x log 1 minus theta. This first derivative, second derivative, just be careful with signs. And then I have to do the negative of that, so everything becomes positive. So now that's what's here, and because this is discrete, I have to sum over the only 2 possibilities little x can be, which is 0 and 1. So when I put in 0, this term becomes 0. This is 1 over 1 minus theta squared. And when x is 0, this thing is going to be 1 minus theta. So I have 1 minus theta over 1 minus theta squared when x is 0. When x is 1, this will appear, right? This will be 1 over theta squared. This will be 1 minus 1, so this will become 0. So when x is 1, f sub x semicolon theta is theta. So I'll have theta over theta squared for x, little x being 1. So I'll just cancel them. Yeah, almost fits there, right? So the expected Fisher information of one sample is 1 over theta, 1 minus theta. This is, so then I have to substitute in theta equals theta n hat to get the estimated standard error, right? So that's what I'm doing next. And these are some details. I'm ignoring the fact that I know there's this indicator function formally, but I'm only summing over 0 and 1 because I don't need to carry that through. Yeah, so SE n hat is just that. So you just worked hard and found out what it is. So just don't forget this n term. So then you put that in, and voila, you get just replace theta by theta n hat. Okay. So And you have to always sit down, take a second, pause, and look at this. Does this make sense? Okay, theta is going to be some number we don't know, right? Theta star, and theta n hat is trying to estimate it, so hopefully it'll be close to it. And then, so this will be some number, right? 0 times 1 minus, so theta times 1 minus theta, and that's the quadratic we saw before. And then we divide that by n, right? So as n increases, this thing is shrinking. It kind of makes sense, because you do want the standard error of the estimator to get small as n goes to infinity, right? And that's the first property, right? So it will get better, and the variance of the estimator itself and the standard error will get small as n gets large. So if you don't have this kind of effect, you got something wrong, right? So here's the final answer. So then I say my 95% confidence interval is just theta n hat plus or minus 2 times this thing that I worked hard for. And then now for this problem, theta n hat, the MLE is just the sample means. So if I ask you, here is a sample of whatever, 50 Bernoullis, zeros and ones, give me the confidence interval, then I don't know, you would, I'm not going to necessarily ask it, but this is a standard problem, right, in your sort of Swedish version of the exams and stuff. Okay, so let us stop here, and I will explain this animation when we come back, and you should not worry about the exam. Okay, just relax. You're stressing me out. It's not going to be hard, and I'll be there.